Welcome to The Explainer. Today we're unpacking a massive transformation happening right now in the tech world. We're looking at the exact blueprints for 2026 to see how messy, isolated machine learning experiments are finally being turned into highly reliable, production-ready systems. If you've ever watched a brilliant AI project just utterly refuse to leave the lab, well, this is absolutely for you. Okay, let's dive right into this. It is the ultimate frustration, isn't it? Why do so many incredibly smart, highly accurate models completely faceplant the second they hit production? Projects just get derailed by deployment failures, or this sudden model drift where predictions literally just fall apart. Taking a model live without a proper system in place isn't just risky, it's honestly like walking a tightrope without a net. The root of this failure usually comes down to a fundamental clash of mindsets. On one side, you've got data science. Their primary goal is model accuracy and rapid experimentation. Think of this like artisan crafting. It's highly specialized, it's meticulous. But on the other side, you have engineering and operations. They care about scalability, performance, and keeping systems online 24/7. That's much more like an automated assembly line. When the artisan hands their delicate custom-built model over to that rigid assembly line, things inevitably break. It's really tough to scale and tensions run high. So here is our architectural blueprint for building that automated assembly line today. We'll be covering bridging the ML gap, core architecture and data, development and CI/CD, model deployment strategies, and monitoring, logging, and governance. Section 1. Bridging the ML gap. The ultimate solution to bridge this huge divide is MLOps, or Machine Learning Operations. It's a structured methodology that seamlessly fuses machine learning with traditional DevOps and data engineering. Instead of just tossing code over a wall and hoping for the best, MLOps creates a vital bridge. It automates workflows, dramatically reduces time to market, and actually lets your data scientists and ops teams collaborate in peace. Section 2. Core Architecture and Data. Let's see how this physical layout comes together. We're looking at a continuous pipeline that makes all of this happen. It kicks off with data collection and pre-processing, basically gathering the raw materials and cleaning them up. That flows directly into model training, where the actual learning happens. Next, we hit deployment, pushing the model out into the real world. And finally, we have monitoring and retraining. But notice how that last step loops right back to the beginning? This isn't a straight line. It is a closed-loop system. When monitoring detects an issue, it automatically triggers retraining, so the system actually gets smarter over time. But here's the thing. None of that pipeline works without data. It is the absolute backbone of any machine learning system. Robust data management is your critical pillar here. You need automated pipelines that reliably handle data ingestion, run strict validation checks, and securely manage storage. You've got to ensure that high-quality, consistent data is always available across your development, testing, and production environments. Which brings us to a real game changer, data versioning. Just like software developers version their code, data teams have to systematically track exact changes to datasets over time. If a model suddenly starts acting erratic in production, you need to be able to hit rewind, reproduce the exact experiment, and audit the behavior. In regulated industries like finance or healthcare, this transparency isn't just nice to have, it's mandatory. Section 3, Development and CI/CD. This is where rapid experimentation meets strict operational control. When a model finally hits those required quality thresholds, it doesn't just sit around on someone's laptop. It graduates to the model registry. Think of this as a highly secure, centralized warehouse. It captures the exact versions, the metadata, and the entire performance history. Only the absolute best models earn their spot here before they ever get promoted to staging or production. Now, to get those models out into the world at lightning speed, we use CI/CD. Continuous integration instantly automates the testing and validation of your data pipelines and training code the second a change is made. Then, continuous deployment takes the baton, automatically releasing those validated models straight into production. It's this snappy automated workflow that prevents downtime and lets your teams adapt instantly. Section 4, Model Deployment Strategies. Because pushing AI out to users is inherently risky. So, how do we safely push these models out? Think of these strategies as your cheat sheet for mitigating risk. You have batch deployment for running predictions at scheduled intervals, perfect for nightly forecasting. You have real-time for instant API responses, which is absolutely crucial for things like catching credit card fraud in milliseconds. Then there are canary deployments, where you release a new model to just a tiny percentage of users to test the water safely. And blue-green deployment, that runs two identical environments, so if the new model fails, you just swap back instantly with zero downtime.
Section 5, Monitoring, Logging, and Governance. The final structural layer that guarantees our system stays healthy.
You see, machine learning models degrade, not because the code rots, but because the real world constantly changes. This is called concept drift. It's when user behavior, market dynamics, or just external factors shift over time. Your model was trained on the past, but it's trying to predict the present. Detecting this concept drift, or sudden shifts in your data, is exactly what triggers those automated retraining workflows we talked about earlier. To actually catch that drift, we have to look at both sides of the coin. First, we must monitor model-specific statistical performance, metrics like accuracy, precision, recall, and F1 score, to know if the predictions are actually still good. But we also have to monitor the operational system health, latency, throughput, and resource utilization. Because if your model is 99% accurate, but takes 10 full seconds to answer a chatbot query, it is still completely failing the user. Alongside all that monitoring, you absolutely need robust logging. This is your historical source of truth. It captures detailed records of inputs, errors, and predictions. Because when something eventually goes wrong, and trust me, it always does, these logs are the only way to do a root cause analysis, reconstruct the past system state, and figure out exactly what happened. Now, to build genuine trust in these systems, core security and governance controls have to be baked right into the architecture. We're talking about locking things down, role-based access control, end-to-end data encryption at rest and in transit, and highly secure artifact storage. When you combine all of that with API authentication and comprehensive audit logs, you guarantee compliance, especially in those heavily regulated industries. To orchestrate this massive, complex architecture, the industry relies on a heavily integrated stack of tools. It's kind of like a giant puzzle. MLflow tracks the experiments and registries, while Docker and Kubernetes package and scale out the deployments. You've got Jenkins driving those CI/CD pipelines, Airflow managing the complex data workflows beneath it all, and Prometheus sitting right on top, keeping a watchful eye on real-time monitoring. So, I want to leave you with this to reflect on. Look closely at your current workflows and the friction between your data scientists and your engineering teams. Is your machine learning infrastructure actually ready for 2026? Adopting these MLOps principles isn't just about getting a single model deployed. It's about building automated, resilient systems that actually last. Thanks so much for exploring these blueprints with me today. Now go build that assembly line.